Calculus class. Today you're going to learn topic 26, how derivatives affect the shape of a graph. And this topic is super important to the AP test. Guarantee you probably about maybe at least 1/5, maybe a quarter of the test deals with this topic. All right, we're going to start with the increasing and decreasing test. A theorem says that if the derivative is greater than 0 on an interval, then f is increasing on that interval. If the derivative is less than 0 on an interval, then f is decreasing on that interval. So, for example, we can find the intervals of increase and decrease on this graph. Notice that the tangent lines have a positive slope. So that means that the derivative is positive here. So the function itself is increasing on this interval. Then as the tangent lines move, they become negative. So then we say that the function is decreasing on this interval. Then at some point, the tangent lines begin to become positive again. So therefore we say that it's increasing on this interval. So we can say that the function is increasing on negative infinity to negative 1 and from 1 to positive infinity because f prime of x is greater than 0 on the intervals. And the function is decreasing on the interval from negative 1 to 1 because f prime of x is less than 0 on the intervals. And this is the type of justification that the AP test would expect in a complete sentence. All right, so let's say we wanted to find the intervals of increase and decrease on this given function. So the first step is to find the critical numbers. So find the derivative, set equal to 0, and if the derivative can be found not to exist at certain values, you also have to do that. In this case, we do not have to because it is a polynomial. Solve for x. So x equals positive and negative 1. Now, set up intervals. A table is a good way to organize all of this. So, we're going to have our intervals. Then you're going to have a test number in those intervals. Then you have to determine the sign of f prime. So plugging that test number into the first derivative. And then the behavior, and then what that looks like on the graph. So my intervals are going to go from negative infinity to negative 1, from negative 1 to 1, and 1 to positive infinity. And I'm getting the 1 and negative 1 from my critical numbers. So now I'm going to pick a test number in each interval. Determine if the derivative is positive or negative. So I'm going to pick negative 2, 0, and 2. You can pick different numbers as long as it's not the endpoints. Now I'm going to plug each of these x values into my derivative, and all I care about is whether or not the derivative is positive or negative. So when I plug in negative 2, I get a negative value out. When I plug in 0, I get a positive value out. When I plug in 2, I get a negative value out. So what that means is that on negative infinity to negative 1, my function's decreasing. From negative 1 to 1, it's increasing. And from 1 to infinity, it's decreasing. And if I really wanted to look at what the graph would look like, it would be decreasing, increasing, decreasing. Now, this is not enough for the AP test. If you want full credit, they want your justification in complete sentences. They will not give you full credit for a table. So step 4 is to write a conclusion and justify your answer. So we can say that f of x is increasing on negative 1 to 1 because f prime of x is greater than 0 on the interval. F of x is decreasing on negative infinity to negative 1 and 1 to infinity because f prime of x is less than 0 on the interval. Let's look at the first derivative test. Suppose that c is a critical number of a continuous function f. If f prime changes from positive to negative at c, then f has a local maximum at c. So it would look like this. So you have a horizontal tangent line, so you know you're going to have either a max or a min. You know you have a max because the slope of the derivative goes from positive to negative. If f prime changes from negative to positive at c, then f has a local minimum at c. And graphically, here's your hill or valley, and you have negative slope to positive slope. If f prime does not change signs at c, that is, f prime is positive or negative on both sides of c, then f has no local minimum or maximum at c. And graphically, this is what it would look like. Something like this. So there is no max or min at c, even though c is still considered a critical number because you have the derivative equal to 0. All right, we are going to find the local maximums and local minimums. This is just like finding the intervals of increase and decrease, but you use the intervals to help you determine which local extrema you have. So let's look at the function cosine squared x minus 2 sine x on the interval from 0 to 2 pi. I'm going to first take the derivative, set the derivative equal to 0, and luckily this derivative exists everywhere. Factor, set each factor equal to 0. I need to find when cosine equals 0, which will be at pi over 2 and 3 pi over 2, and I only have to stay within my given interval. And I need to find when sine x is negative 1, which is x equals 3 pi over 2. So now I'm going to set up a table, just like I did with the the increase-decreasing test, but I have an extra row here to tell me whether or not I have a min or a max. So my intervals are going to go from 0 to pi over 2, pi over 2 to 3 pi over 2, 3 pi over 2 to 2 pi. Now I'm going to pick a test number in each one of these intervals. So I'm going to choose x equals 1, 2, and 6. I'm going to go ahead and plug in each one of these values into my first derivative. When I do that, I only care about the sign. So from 0 to pi over 2, I get a negative value. From pi over 2 to 3 pi over 2, I get a positive. And from 3 pi over 2 to 2 pi, I get a negative. So this tells me that the graph is decreasing, then increasing, then decreasing. So if I was to sketch this, the graph decreases, then turns and increases, and then turns and decreases. So that means I'm looking at local extrema at each of the critical values, pi over 2 and 3 pi over 2. Well, at pi over 2, the function is going from decrease to increase. In other words, the derivative changes from negative to positive, which means that I have a minimum. Then at 3 pi over 2, the function's increasing and then decreasing, which means the derivative is changing from positive to negative, so I have a maximum. Now I'm going to have to justify my reasoning. So I would say that there is a local minimum at pi over 2, comma negative 2, because f prime of x changes from negative to positive at x equals pi over 2. There is a local maximum at 3 pi over 2, comma 2, because f prime of x changes from positive to negative at x equals 3 pi over 2. Okay, now let's look at the second derivative test. Now, the first derivative test allowed us to determine local maxes and local mins. The second derivative test does the same. Sometimes the second derivative test is a lot easier, sometimes it's not. All right, so suppose f double prime is continuous near c. Then, if f prime of c equals 0, and f double prime of C is greater than 0, then f has a local min at C. So what that means is if I was to have a critical number at C, which means I have a horizontal tangent line, and if the second derivative is positive, so that means if I was to take the second derivative and plug in the critical number and I get a positive value out, then I have a local minimum. So this means that the function is above the horizontal tangent line. And here's a little helpful thing, is if you get positive values, you get a smiley face. So that means you have a minimum if you were to draw a horizontal tangent line. Now, if f prime of C equals 0 and f double prime of C is negative, then f has a local maximum at C. So if we look at this example, this means that the function is below the horizontal tangent line. So if you want to stick with the faces, so pluses mean a smile and a minimum. Negative means a frowny face, maximum, if you were to draw a little tangent line on the frowny face. So let's find the local maxes and the local mins using the second derivative test of x cubed minus 27x. So I'm going to first find the critical numbers. 3x squared minus 27 gives me my derivative. Set my derivative equal to 0. Luckily it's a polynomial, so I don't have to worry about where it doesn't exist. Solve for x. So I get x equals 3 and negative 3. Now I'm going to find the second derivative. So second derivative is 6x. Now I'm going to evaluate each of the critical numbers in the second derivative, and I'm looking to see what sign I get when I plug them in. So my critical numbers are negative 3 and 3. So when I plug negative 3 into my second derivative, I get a negative value out. When I plug in 3 to my second derivative, I get a positive value out. That means since I got a negative value out, I'm going to have a maximum. And if I was going to plug in an x equals 3 gives me a minimum. So the justification that I would use to write my answer would be that there is a local maximum at negative 3, 54 because f double prime is negative at x equals negative 3. There is a local minimum at 3, negative 54 because f double prime is positive at x equals 3. Now I like the second derivative test when it's easy to find the second derivative. Sometimes it's not easy to find the second derivative, so then I wouldn't even attempt the second derivative test and I would just stick with the first derivative test. Now this leads into concavity. If the graph of f lies above all of its tangents on an interval, then it is called concave upward on that interval. If the graph of f lies below all of its tangents on an interval, then it is called concave downward on that interval. So here are some sketches of concave upward. So it is above the tangent lines. Concave downward is below the tangent lines. So the concavity test. If f double prime is greater than 0 for all x in an interval, then the graph of f is concave upward on the interval. If f double prime is less than 0 for all x in an interval, then the graph of f is concave downward on the interval. So here's concave upward. There's two different ones. Notice that the second derivative is positive, which means that the function itself is above the tangent lines. And then concave downward, the function is below the tangent lines. And this also works with our little smiley face, because if you were to have plus smiley face, that is concave upward, the second derivative is positive. If you're to have minus minus and a frowny face, you have concave downward, and the second derivative is negative. So with this one, f is increasing and f is decreasing, but they're both concave upward. F is increasing, f is decreasing, but both concave downward. Here, f prime is greater than 0 and increasing. F prime is less than 0 and increasing. F prime is greater than 0 and decreasing. And f prime is less than 0 and decreasing. This leads into what we call inflection points. So a point P on a curve y equals f of x is called an inflection point if f is continuous at P and the curve changes from concave upward to concave downward, or from concave downward to concave upward at P. So inflection points can occur when f double prime is equal to 0 or does not exist. And f double prime changes from positive to negative at P. F double prime changes from negative to positive at P. And if f double prime does not change signs at P, that is, f double prime is positive or negative on both sides of P, then f has no inflection point at P. So here's an example. Here you have concave upward, and then at some point the graph changes direction, and we have an inflection point, and it becomes concave downward. And here's another graphical example as well to see concave up, inflection point, concave down, and so on. All right, on this graph, I want you to estimate the points of inflection and the intervals of concavity. So inflection points, it should be at x equals negative 0.6, so it's changing from concave up to concave down. X equals 0, concave down to concave up. X equals 0.7, concave up to concave down. So now this allows me to do my intervals of concavity. So concave upward is from negative infinity to negative 0.6, and from 0 to 0.7. Concave down is from negative 0.6 to 0 and 0.7 to positive infinity. Now we're going to find the points of inflection and intervals of concavity on the given function x to the fourth plus 6x cubed. So your step 1 is to find the inflection numbers, which means find the second derivative. So I find the first derivative, find the second derivative. Then find where the second derivative is 0 and does not exist. And in this case, since the second derivative is a polynomial, it exists everywhere. So we're only concerned about when it's equal to 0. I can factor out a 12x. So set each factor equal to 0. X equals 0. X equals negative 3. So these are my possible inflection points. So now I'm going to set up test intervals and choose a test number in each interval. Determine if the second derivative is positive or negative. I'm going to set up my table, and I have my intervals, negative infinity to negative 3, negative 3 to 0, and 0 to infinity. Now I'm going to pick a test number in each interval. So I'm going to choose negative 4, negative 1, and 1. Now I plug in each of these x values into the second derivative, and I look at the sign. So I plug in negative 4, I get a positive. Negative 1, I get a negative. And on 1, I get a positive. So what this tells me is that f is concave up on this interval, concave down on this interval, and concave up on this interval. So if I wanted to sketch what this looks like, that means concave up, concave down, concave up. So since I am changing concavity, so I'm changing from concave up to concave down at -3, that means I do have a point of inflection at -3. And since I'm changing from concave down to concave up at 0, I do have another point of inflection. And then the last step is to write your conclusion and justify your answer. So I would say that f of x is concave up on -infinity to -3, and from 0 to infinity, because f double prime is positive on the interval. F of x is concave down on -3 to 0, because f double prime is less than 0 on the interval. And there are points of inflection at -3, -81, and 0, 0, because f double prime changes sign at x equals -3 and x equals 0. All right, your turn. So you are going to find the following and give justification for each on this function. So go ahead and pause, and this will probably take you a good 5 to 10 minutes plus. All right, let's see how we did. So first find the first derivative. I'm going to set the first derivative equal to 0. Since it's a polynomial, I do not have to worry about does not exist. Find my critical numbers. So factor out a 6. 6 can cancel, so I'm left with 3 and -2. And I'm going to go ahead and get out of the way my second derivative and possible points of inflection. So I found the second derivative, set it equal to 0. Doesn't matter if it doesn't exist because it's a polynomial. Solve for x. So x equals 1/2. Now I'm going to set up a nice big table with my intervals. So I'm going to first deal with the local extrema here and whether or not it's increasing or decreasing. And then I'll deal with the points of inflection down here. So for the possible local extrema, my critical numbers are -2 and 3. So I set up my intervals accordingly. I'm going to pick a number within each interval, plug it in to the first derivative. So when I do that, I would get a positive first derivative, a negative first derivative, and then a positive first derivative. So this tells me that my graph is increasing, decreasing, and then increasing. Now for local extrema, since I'm going from positive to negative, that means I have a maximum at -2. And since I'm going from negative to positive, I have a minimum at 3. Now I'm going to deal with the second derivative intervals, which is going from -infinity to 1/2 and 1/2 to infinity. So I'm going to pick a value in each of these intervals, plug it into the second derivative to figure out the sign. So I get a negative second derivative and then a positive second derivative. What this is telling me is that my graph is concave down and then my graph is concave up. Since I am changing concavity at 1/2, that means yes, at x equals 1/2, I do have a point of inflection. Now I'm going to go ahead and justify what I have just analyzed. So I can say that f of x is increasing on -infinity to -2 and 3 to infinity because f prime is greater than 0 on the interval. F of x is decreasing on -2 to 3 because f prime of x is less than 0 on the interval. There is a local minimum at 3, -74 because f prime of x changes from negative to positive at x equals 3. There is a local maximum at -2, 51 because f prime of x changes from positive to negative at x equals -2. F of x is concave up on 1/2 to positive infinity because f double prime is greater than 0 on the interval. F of x is concave down on -infinity to 1/2 because f double prime is less than 0 on the interval. And there is a point of inflection at 1/2, -23/2 because f double prime changes sign at x equals 1/2. All right, analyzing graphs. So the given graph is of the derivative of the function f. So this is the graph of the derivative. Find where f is increasing and decreasing and justify your answers. So f is increasing on negative infinity to negative 2 and 0 to infinity because f prime is greater than 0 on the interval. So since this is the graph of the derivative, that means I know it's the graph of the original is increasing when this graph is positive. So that's what I found. I found that it was positive or above the x-axis from negative infinity to negative 2 and above the x-axis from 0 to positive infinity. F is decreasing from negative 2 to 0 because f prime is less than 0 on the interval. So the graph of the derivative is below the x-axis. Find all local maximum and local minimum of f and justify your answer. So x equals negative 2 is a local maximum because f prime of x equals 0, right? So that means we have a horizontal tangent line at negative 2 on the original, and it is changing from positive to negative. So it's crossing the x-axis, and it's going from a positive value to a negative value. So that tells me on my original graph I have a local max. At x equals 0 is a local min because f prime of 0 is equal to 0 and is changing from negative to positive. Now I'm going to find intervals of concavity and inflection points and justify your answer. So f is concave upward on negative 1 to 1 and 2 to infinity because f prime is increasing on that interval and f double prime is greater than 0 on the interval. So given the graph of the first derivative, the original graph is concave upward when the first derivative's graph is increasing. So that's what I did, is I found when is this graph increasing. This graph is increasing from negative 1 to 1 and from 2 to infinity. This is also where if I was to draw tangent lines on this graph, and those tangent lines would represent the second derivative, would be positive slopes. F is concave downward from negative infinity to negative 1 and from 1 to 2 because f prime is decreasing on the interval and f double prime, so the little tangent lines on f prime, are negative. And x equals negative 1 is a point of inflection because f double prime would equal 0. You have a horizontal tangent line on f prime, and f prime is changing from decreasing to increasing. X equals 1 is also a point of inflection because you have f double prime would be 0, you have a horizontal tangent line, and f prime is changing from increasing to decreasing, so it's changing concavity on the original. And then finally, x equals 2 is another point of inflection because f double prime is 0 and f prime is changing from decreasing to increasing. Well, I hope you enjoyed learning about how derivatives affect graphs of functions, and this stuff will be practiced for the rest of the school year. Have a good night.